Um, wait, is it recording? Okay, yeah, I think it's recording. Yeah.
Yeah.
Okay, so yeah, you can't only double one thing. You have to double everything. And trust me, it'll make everything in Hess's law make more sense too.
So what is Hess's
Yeah.
law?
So I was about to get to that. So now that you
Okay.
understand the manipulations of these things, you can understand how they come together to make Hess's law. So Hess's law problems are kind of puzzles. So do you see this equation over here? Calculate the entropy
Yeah.
for this reaction. So that's what we're trying to do over here. So we're trying to get this reaction and find the enthalpy of it based on these things that we already know. So let's say like scientists already found these three reactions. And they found out that the energy released by them is exactly this amount. So based on this, can we use them to calculate this? So you know in math, there's like those things that are like 2x plus 4 is equal to like 6 or something, or plus 4y equals 6. And there's like x plus 3y equals 7. Like what is x and y? Remember like how you double
It's
this
like
entire equation?
elimination or like
Yeah, elimination.
substitution.
Yeah. That's basically
Yeah.
what Hess's law is, except with like chemicals instead of x and y's. But then they're also like pretty easy too. So here's the steps I recommend to rearrange these. So it's basically three equations, and you're at the end, you're like adding them all up and then having them equal to this. So this should equal to 2C plus H2, like that type of stuff. Get it?
Okay, so
Yeah. So now
yeah.
let's so now let me take you through the steps. I'll show you how to approach this problem, then I'll let you do the other one, okay?
Okay.
Okay. So calculate the enthalpy for this reaction. So the first thing I'd like to do is find the unique things in this. So let's look at this, right? What here are doubles? There's O2 over here and O2 over here.
Yeah.
So those are doubles. So I don't like those. Is this unique? The C2H2? Does this appear anywhere else?
Well, H2 is already below there, but does that matter? Because there's both C and H2.
Yeah, this is a different chemical than just H2.
Okay.
So this is one unique thing. Okay, I'll circle that. What about CO2?
No, there's another CO2 there.
H2O?
H2O,
No.
yeah.
What about C?
C, there's nothing else. There's C2, but
Okay,
they're
I'll circle
different.
that.
Okay.
What about H2?
H2, that's H2 is not, there's no other thing.
Yeah, so these are
And that's
unique, right?
yeah, just those
Now
three.
let's look at it this way, okay? If we were to add all of these up, they would need to cancel, like basically these Hess's law problems, they'll give them to you so that they'll perfectly cancel out to get this, if you arrange it properly. So let's look at what's in the reactants, right? The reactants, there's 2C. So which reaction had the unique C in it?
The second one.
The second one, right? So how do you think you'd make two of them?
You multiply by 2.
Okay, so I'll write times 2. And then in order to make things pretty easy, on the right side, I'll write the reaction multiplied by 2. So 2C plus 2O2 yields 2CO2. Agreed?
2C plus 2.
That's double of this,
Yeah.
right? Okay. So now let's look at the next thing, H2. Which one of these has H2?
The third one.
The third one. Are they matching?
Oh yeah, they're matching.
Yeah, perfect. So that's just times 1, no change. Okay, what about this other one?
Yeah, that's in the first one. And
What
they
do you think we
match.
should do?
They're matched, so you just take negative 1299.5.
Yep, because you need to make this one end up on the right side. So you have to multiply this by -1.
Oh, okay.
Okay, so I'll write that times -1. So it'll be H2O plus 2CO2 yields C2H2 plus 5 over 2O2. Okay, and this one was just the H2 plus 1 over 2O2 yields H2O. Okay, so now let's look at this. So do you see how this is on the left and the right side?
Mm-hmm.
That means it cancels out. Good?
Yeah.
So this is just like a Hess's law type of thing. Okay. So on the left side, there's 2CO2. There's also 2CO2 on the right side. Do you see that?
Yeah.
Cancel out. Do you see how there is some O2s over here, and there's like some O2s over here?
Yeah.
So what do you think these two add up to be together?
2.5 O2, and which is the same thing as 5 2 over O2, so you can just cancel them out.
Good. Now what do you think it ends up as? The final reaction.
2CH2 did the same thing, right? So they add up to 2CH2, so don't you just cancel it out?
Wait, what?
Because 2C
No, no, no,
plus,
no. These are different reactants.
okay,
Like just think of them in real life. Like a bunch of carbons would look like a diamond. A
yeah,
bunch of H2 would look like gas, and a bunch of C2H2 would look like some liquid on the ground or like some gas.
okay. So it's 2C plus H2. Oh, yeah, there'd only be if they're multiplying, right? Yeah. So 2C plus H2 equals C2H2.
Okay, now do you see how we came up with these are varied? So this times -1 is 1299.5, right?
Mm-hmm.
This times 2 is negative 787, right? This one is something 0.6 times 2, 1, 16, 17, 4, 5, negative 571.6, right?
Isn't it times 1 though?
Oh, wait, oops.
Yeah.
I multiplied by 2 by accident.
Mm.
Perfect. So now these, you add them all up and you get some answer. And that is the enthalpy of this reaction.
Then what was the point of doing the stuff on the right?
What?
The 2C plus H2 equals C2H2. If you didn't need that, what was the point of doing that?
That's the same as this. It's just showing that these, like the manipulations that we did were correct.
Oh, okay.
If we
But
did
do I
this
have
like
to,
wrong, right? Instead of multiplying this by 2, let's say we multiply by 3. We'd get like 3 of this, and then the O2s wouldn't cancel out, because now it'd be like too much. And then the CO2s wouldn't cancel out either. So do you
do
see
I
how
have,
this method of going through the unique reactants and products and then matching them up with this? Do you see how that kind of helps
yeah, but you
the
don't need to do
manipulations?
that, right?
What?
You don't need to do that though, right?
Yeah, you do. So this is
No, I
very
mean the thing
easy.
on the right. I mean like making sure that part. You
Oh,
don't need to
this?
do that, right? Yeah.
This was to demonstrate it to you, but in higher level hess law problems, you need to do this in order to make sure that you know what's going on.
Okay.
You'll see what we mean, but when we move to this second one. Okay, let's go to number 2. Okay,
Okay.
so in this one,
Should I
let's see
do
what we
this one?
have. So can you tell me the unique everything?
Okay. So C. SS is actually no, it's not. It's not just two SS. O2 CO. CO only the stuff on the right, right? CO2, SO2, and CSO2. Those are the only unique
Is
stuff, I think.
SO2 unique? Is CS2
It's-
unique? Yeah, wait, this is unique.
yeah.
So, okay, now let me tell you the second layer of information. When you have all 3 of them being unique, it's really easy. Because as long as you manipulate these 3 to be the correct things, so for example, let's go at CO2. What do you think they should do to this one?
You CO2, you just keep it the same.
Yeah. Okay, what about this one?
SO2 multiplied by 2.
Yep. So now it should
CS,
end up as this, right? What do you think you did to this?
you multiply by 1.
By 1?
Yeah, this is by 1. Same thing, right?
By 1?
It's the same thing, right? CS2, it's the same.
Read it carefully. Where's CS2
Oh,
in
it's
the
on the
reaction?
other side, so should I make it negative?
Yeah, so that's another thing that helps out. Like if you were to make a mistake, then writing out the things on the right side will make it much easier to fix that mistake because you'll realize something is wrong.
Okay, so
Yeah,
if
but as
it's
long
if
as you
it's on
have
the
this clear vision of where everything should go and the exact manipulations that you should do and you don't mess up, and there's 3 of them that you know, then you should be fine.
okay,
So
so
like at the end of the day, right? It's a chemistry problem. They're not going to do some insane, impossible stuff. So as long as you make these sort out into the right places, this O2 will kind of just like fall into place.
okay,
Yeah. So with this problem, you just like write these out, what they would be equal to, and then add them up. Got it?
okay, okay,
Okay. I think number 3 gets harder. Okay. So calculate. Yeah, they tell you the reaction at the bottom that you need to calculate. So again, what's unique?
okay. Uh, uh, CO2.
CO2. Okay, yeah.
Yeah. S-
SRO.
SR. No, it's not. 2SR. No, 2. So 2SR. 2C, and I think that's it.
Okay, yeah.
Okay.
So now do
And
you see how there's only two things?
yeah.
So that means we have to show our work to find out what to do with the third thing. But let's start with these two, okay?
Okay.
So CO2, what do you think we should do to that?
CO2, it's negative.
Yep,
So,
times negative 1
yeah. And CSER just times 1.
times 1.
Yeah. No, sorry, times 2, times 2.
So where are you trying to make the C end up?
What do you mean?
Like
Like
it's 2C over here on the products. Where are we trying to get it to?
to the CO2?
No. Where else does C match up in like what we need to get to? Okay, like what you have to realize is that these are all individual products, individual reactants. C is not the same thing as CO2. C is only the
Okay.
same as C. Like maybe you could color code each thing. Like this is X. Like this one is X. Like maybe all the CO2s are Ys or something like that. Just don't confuse these things. Like I get that this CO2 also has a C, but it's not the same thing as this at all.
Okay.
This right here is a diamond. This right here is in the air. Like they're very different.
Okay.
So where are you trying to make this 2C end up? And what are you trying to make it be?
So 2C, I don't stint to 2 SRCO3, is that what you mean?
No, okay, look. So remember in these other reactions that we had? Like for example, in this one, we tried getting the unique ones were all these, right?
Mm-hmm.
But this one was easy. There's not that much that we need to do. We just needed to find out whether it was still in the products or like this one we have to multiply by 2, right? Because there's 1 here, there's 2 here,
Mm-hmm.
right? This one, we have to flip it, make it go to the reactant side. That's why we did times 2 here and then times negative 1 here, right?
Mm-hmm.
Well, now, if you have something that needs to end up, oh wait, was this the one we're doing? No, it wasn't. It was this one,
3.
right?
Yeah.
Okay, yeah. So the unique ones were what again?
Uh,
SRO? No, it
uh,
wasn't. CO2? No, it wasn't.
S
Well, yeah, it was CO2 and it
and
was C,
2C.
right? I think there's no
2C.
others.
Yeah. That's it.
O2, SR, CO3. Yeah, that's it. So we've already sorted out this one. This one needs to flip to go to the
Oh,
products.
you mean where it goes in the other thing? Oh, so it becomes 1/2, right?
Just one
Okay.
half?
Plus,
Okay,
yeah, just one.
let me write down this reaction as if it was times 1/2, okay?
Okay.
SrCO3 yields Sr plus C plus 3 over 2 O2. Does that look right? Is that what we want?
C plus, yeah.
Okay, sure. Let me keep this to demonstrate like the problems with it. This one was times negative 1, right? So
Mm-hmm.
SrCO3 yields SrO plus CO2. You understand how I did this, right? I just flipped it because it's times negative 1. So
Couldn't you multiply?
I want you to try being able to imagine these manipulations. So times 1/2. Can you imagine that in your brain? Like look at this and imagine how a times 1/2 would look like.
What do you mean by imagine it? Like the
Like
reaction?
basically imagine like this. Like, okay, just go step by step. If it's times 1/2, this will turn into a 1, right?
Mm-hmm.
This will turn into a 1.
Mm-hmm.
This will turn into 1. This will turn into a 3 over 2. That's what I mean by imagine.
Yeah.
When you're trying to figure out what manipulations you should do. So now try to ask yourself this question. Where are you trying to get this to end up? Like, can you tell me everything about the C's location?
It's on the left.
It's on the left, okay. and it is just a singular C.
Mm-hmm.
So you solve the
One
problem of it
mole.
being a singular C. You solve this problem.
Yeah.
Is there any other problems we need to solve about this?
The O2, right?
No, no, no. Just look at only the C, okay? What
Okay.
side is it on?
This is on the left side.
No, this is on the right side.
Hmm? Oh, wait, what? Oh, on for that C, yeah.
You're trying to make it end up there, right?
Oh, if you want to make it on the oh, just negative
Yep.
1/2.
So let me erase all those.
Oh, so you need to make it like where it is on the original one?
Yep.
I see.
Okay. So now -1/2. Can you tell me what the reaction would look like as -1 times -1/2? What should I write down?
Okay, you make it uh SR plus C plus 3/2O2 equals SrCO3.
Okay, good job. Okay. So now we've solved these two problems. We've solved the C and we've solved the CO2, right? So those are checked off. Now we only need to solve this problem of the O2. So how do we manipulate this so that after all the canceling, there's only one O2 left on the left side? So let's look at this so far. So on the left side of this reaction, how many O2s do we have?
Of which one?
Okay, can you imagine like the combined version of these two reactions now? Let me write it down for you.
Yeah, it'd be like 2SrCO3
No, 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 no,
equal.
no, no. The combined version of these two. So there's SrCO3 on both sides, right?
Yeah, so once you just do 2 of that equals, and then you add both the things over there, right?
Wait, hold up.
I know you come. Oh, that's not doing
So these two are finalized. We are not changing these two. Agreed?
it.
If we change these two, then we're going to mess up the positioning of the
I'm
CO2,
thinking.
and we're going to mess up the positioning of the C. Do you agree with that?
Yeah. So it's
These are solid,
SR
which
plus.
means we can cancel out. So remember in the other
Yeah.
ones, we canceled stuff out if it was on the
Yeah.
opposite sides?
Yeah.
So we're going to cancel these two out. Do you see that?
Yeah. So it's SR plus C plus 3/2 O2 equals SRO plus CO2.
Right? So this is the added up reaction now.
Mm-hmm.
Okay. So now how do we make it so that we end up with one O2 on the left side? What should we do to this one?
Divide it by 3/2.
3/2? So if we multiply, okay, think of everything in terms of multiplying, I'd say.
Multiply by 2/3.
2/3. So what would the okay, so yeah, what would you get if you multiply this by 2/3?
If you multiply what by like the second equation?
Yeah, the second equation.
You would make it 2/3 SRO.
No. What's
Wait.
2 times 2/3?
Oh, that's 3. I mean 2. Wait. 3
What is
times
this?
3. 3 times 3. 2. That's 4/5.
4/5.
Yeah.
It's
At
4 over 3.
4/3. I'm stupid. I meant to say. I meant to say 3, but I accidentally said 5.
Okay, good. So that's 4/3, right? So you're
Yeah.
left with 4/3 SRO. By the way, do you still want to continue down this path?
Yeah.
Or do you want to change this number? Okay, sure. Let's continue.
No, why would you change it?
Okay. What's 2 times 2/3?
Sorry, what 2 times 2/3?
Yeah,
That
what,
is
what
four
would this
over
turn out to?
three. 2 times 2/3 is 4/3, right?
So 4/3. So tell me what to write on this side now.
4/3 SR plus 2/3 O2.
Okay. Yeah. So now does this cancel out to perfectly 1?
It doesn't cancel out.
It doesn't cancel out, which means we did
No.
this wrong.
Yeah.
Which means that the manipulation was not times 2/3.
Mm.
Okay, in general, you're not gonna like divide things by 3. Like in general, it's gonna be like even numbers like 2
Wait, did I say? Wait, wasn't supposed to be 4 out over 3?
times 4 over 3.
Yeah. Wait,
Okay,
wait. No,
but then
times 2 over 3, but the things over there were supposed to be 4 over 3, but I said 2
okay,
over
look,
3.
here's what you need to look for. So you know how we're trying to deal with only the oxygen? Everything else will
Mm-hmm.
fall in line. If we deal with the oxygen properly, everything else will fall in line.
Mm-hmm.
So how do we manipulate this oxygen and this oxygen over here so that they cancel out to be exactly 1? So
Using
how
the
many oxygens do we need to subtract from here?
3 over 2.
If we subtract 3 over 2 oxygen, so let's say we end up with 3 over 2 O2 over here, then they would completely cancel out, right?
Yeah.
Do we want them to completely cancel out?
Yeah.
No,
No.
we're trying to end up with 1.
Yeah. So it's 3 over 2. We just want 3 over 2.
Then it would
Right?
cancel out to be 0.
Oh. So we want 2 over 3?
Okay, what's 2 over 3 minus 3 over 2? What is this?
Wait, minus. Oh, wait,
It's
what?
this minus this. Or like, yeah.
So that's 4 over 6 times 9 minus 9 over 6. That's
4 over
negative 5 minus 9 over 6, right? So that
yeah.
would be negative 5 over 6.
Is that anywhere close to 3 over 2?
No.
Okay, so think of it mathematically, okay? X, okay,
Oh,
I'll
wait.
do this in
Oh, yeah. I know. It's 5 over 2, isn't it?
X minus 3 over 2 is equal to,
5 over 2.
no, actually,
Wait.
no.
1.
It should be, okay, yeah. Okay, 3 over 2 minus X is equal to uh 2 over 2.
So also the 1 over 2?
Yeah, if you have
Oh.
a 1 over 2 on this side, that means that, do you see how only 1/2 of it will cancel out now?
Mm-hmm.
So this 3 over 2 minus the 1/2 over 2 will result in a 2 over 2 O2. Do you see that?
Mm-hmm.
Okay. So how do we make it so that there's 1 over 2 O2 here?
Okay.
How do you make it so it's like that? What do you do to this one?
You make it 2 over.
What?
I'm so confused. Wait. Can you make it 2 over 2?
Times 2 over 2?
No, wait. Oh, like over there. Oh, you just make it times, uh, you just make it times 1 over 2, right?
Yep, perfect. That will make this into a 1 over 2 O2, right?
Yes.
So can you tell me the rest of the reaction just to make sure that you know how to do this?
Okay. It would be SRO equals SR plus 1/2 O2.
Yeah. Okay. So now do you get the manipulations?
Mm-hmm.
Why we did each of them? So just to recap, we did these first two in order to, because like they're solidified. We cannot change these reactions because this CO2 needs to end up on the right side. So it has to be -1 because there's nothing else that can cancel out to get that CO2 perfectly like that. This one had to be times -1/2 because it needed to perfectly go, because like the negative, so it goes on the left side first of all, and then the half so that this 2 turns into a 1. Okay? And then after that, we wrote the reactions. We found out this becomes like 3 over 2 O2 over here, but we're trying to get it to 1. So think about what we have and what we're trying to get to. That's a big part of Hess's law problems. So we're trying to get this to 1/2 to 2 over 2, which is the same thing as 1, right? So that's why we realized that we had to make this. We had to somehow get a half oxygen on the right side of the equation. And once we realized that, it was pretty easy to find out the manipulation you have to do to this.
Mm-hmm.
Yep. So you find these numbers. This would be like 234, like positive. This one would be half of that. So like 592, right? Positive 592. This one would be negative half of that. So negative 1220. and then you add these three numbers and you get a number. I'm not gonna do it right now because it's a waste of time. But and then that's your answer in kilojoules.
Okay.
Got it?
Yeah.
Okay, yeah. So you could watch over this recording later. I'll post it on YouTube probably because I can't post a big attachment like that on the messenger chat.
Okay.
Okay. So number 4. This time I'll make you do a lot more of the content.
Okay.
So what's the first step?
Oh, I hate chemistry.
No, okay, these ones are actually kind of fun. They're puzzles.
My head is I'm tired.
Yeah, I know. This time it's only you. I can't I can give you the breaks by talking to Vikita, you know?
Uh, okay, so first step is okay, you find the loners, right?
Yay, the
Uniqueness.
lowers.
All right. Um. So, and
No, no.
no. Okay. H2O is a loner. He
Okay.
doesn't have any friends, and and that's it. What? That's it.
In general, they'll always give you 2 loners. They'll either give
Okay.
you 2 or 3 loners.
Okay.
If there's 3 loners, it's easy, but then 2 loners, you have to kind of work around it. But there's one other thing. Always keep looking until you find 2, or maybe 3. But
Is it because is it NO2? Because NO and NO2 are different?
yep, this one's a different one. Is there anything else?
No, get it, but crash.
Wow, so original. There's one more.
O2 are the same. There's NO
You could
already.
even note them down. You'd be
N2.
like, oh,
No, they're all. Oh, the on the right side, HNO. I didn't look at the right side.
this one, right?
Yes.
N2,
No,
O2 again. So yeah. So I make all these symbols to make the matching game. It's kind of fun. Okay. So these are our 3 loners. But then do you see how these 2 loners are in the same line? That means technically I don't even care about that thing. I'm just trying to sort out these 2 lines. Okay, so what do you think we should do the first one?
With the first loner, we see it, look at in the other thingy, so we multiply by 3, cap.
Like that?
Yeah, no, but just wait. Oh, wait, 3/2. Yeah, by 3/2. And then H2O, we do
Are
one
you sure
half.
that's it?
Oh,
Are you sure? Be very careful about this step in particular.
oh, negative.
Negative. That entire thing
Ye-
could have screwed up your whole problem.
Yeah. Okay. Now 2H2O, they're both on the left, so one half. No cap.
So what should I multiply by?
One half.
Okay, good.
Okay, and now it's the 4, blah, blah. So we do one half again since it's on the right.
This one? We can't do
Why?
anything for this one yet because we don't know. There's nothing that it should end up because do you see how there's no loners? That
But
means
isn't HNO loner?
this one?
Yeah.
But that's in the same reaction as this. If you multiply this by half, it ends up perfectly as
Oh,
this.
yeah.
That's why I didn't really care about it. I knew that it would sort out because chemistry problems sort out. If you
Okay.
sort out if you sort out the H2O, you're solving the whole problems in this line. If you sort out the NO2, you're solving all the problems in this line.
So
I
now
would
you
say
have
the
to
hardest one
do.
about this is the NO2.
So since you got the only two, you have to do the stupid 50-minute long thing.
Yeah, exactly. So can you tell me what this is?
Okay. First, you would do so times -3/2, right? So that would be I can't do. So 2 of -3/2. So that's -6/2. So that's -3, right? Wait,
Yeah.
no, I'm stupid. But this so he's moving to the other side. Okay, so it's okay. So so it's the first would be 3 NO2.
Okay, good.
right?
Good.
All right, equals 3 NO plus 3 over 2 O2.
Perfect. Good job. Okay, the second line.
All right. Times 1/2, right? So that'd be N2 plus 2 to 5 5 over 2. Just say that. So N2 plus 5 over 2 O2 plus H2O equals 2NO3.
2HNO3.
Yeah.
Be very careful about this. Like, there's a lot of places you can mess up.
Now we just write do you write the third one? Yeah, right. And then we
Okay.
find
Or you
out.
can mentally think of it this way. You could be like, okay, I sorted these ones, and I ended up with like the NO2 here.
Mm-hmm.
I ended up with so this one's check, right? I ended up with the HNO3. That one's also check, right? Because that was a unique one. I
Mm-hmm.
ended up with the O2. What's left that I need to sort out?
Okay, NOG, no cap.
No, that's the last one.
No, yes, no.
So how much do we have already on the right
We
side?
need to find 2 NO, right? So we
So
can subtract it.
how many
Oh,
do
no,
we
wait,
have on the
since
right
it's on
side
the
so
right
far?
side, sorry, we need 4 NO, right?
So
Because we
there's
have
3
on
here
the right.
already.
Yeah. So we
How do we
need
make it
4.
so there's only 2? There's only 1 now.
We find 4, so because we do 4 minus 3, right?
Yeah. Wait. Are you sure? So look, do you see how we need to end up with NO on the right side?
Yeah.
Is this already on the right side?
Yeah.
Okay. So in order to get to only 1 on the right side left, how many would we need to cancel from here?
2.
Yeah, so we have 3 over here. We need to cancel out 2.
Okay.
So do you see what that means?
If it was on the other side, would it be 4?
Yeah. So if you had like 3 NO over here, that means we need to add 4 more over here in
Oh, it's
order
like
for this
adding.
to be gone and this to be 1 left. Do you see that?
Yeah.
But since there's a greater number, there should be a greater number on the right side than the left side. Do you see that?
Okay. Yeah.
So how many should we try getting over here?
2. I
Okay.
know.
So there should be 2 NO here. Perfect.
Mm-hmm.
How do we get this so there's 2 NO on the left side?
Oh, you just make it a -1.
Okay, perfect. And then that should work out. So we did that -1. So 2 NO. Can you tell me the rest?
All right, I'm so cool. Equals uh uh this other thing N2 plus O2, right?
Yep. Now, do you want to see if it works out or
Yes, let's see.
okay, this will be satisfying. Okay. So 3 on O2, this one was check, right?
Yes.
H2, that one was a check. Those were individual ones. This one was also an individual one. So now everything else kind of cancels out. So first of all, this 2 and O will cancel out. This will become a 1. Okay. Let's look at this N2.
What do you mean by individual ones?
If you have 2 on this side and you have 3 on this side, this is going to cancel out. So you only have 1 of this left, right?
Wait.
No, I'm talking
What?
about the loners.
Yeah.
So I already know because these are loners, they're not going to get canceled with anything. So I put a check mark on top of that.
Oh yeah, because they're from the previous thing, right? Yeah.
There are these 3. So I put check marks.
E.
There's no need to deal with them. They're not going to cancel with
Mm-hmm.
anything, so there's no need to worry. So what about everything else?
All right. So okay. N2 was over there. Those two cancel out.
The N2s? Okay, good.
Yeah. But then what about O2? And then there's 5 over 2 O. Oh yeah. So O2 plus 3 over 2 O2 equals 5 over 2 O2, which you cancel out. And then you have 2 NO equals 3 NO. Is that
Do you remember why we set this as 2?
because it's -1, right?
Okay, let me write it this way. This will be easier. There was 2 over here, right?
Yeah.
We have 3 on the right side. We have 2 on the left side. So This one will cancel out with this one or something. This one
Oh
will
yeah,
cancel out.
because we minus them.
See with
Yeah.
that? And that's why we end up with NO at the end over here.
Oh, I'm so cool.
Yep. You're hella cool, dude. So
I'm
yeah,
the most.
the final reaction, let's see what's left on the left side. On the
Nothing,
left side,
right?
you have 3 NO2.
Oh, the loners. Yeah.
You have 1 H2O. And on the right side, you have what?
2H, NO3, and NO. I'm so cool. Oh my god.
I know, dude. See how these are kind of fun?
That makes me suffer.
It makes you feel like start playing like that like the dune 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 dune.
It's like, yo, I got a question wrong. Now my suffering's over. Oh, wait, there's 10 more.
Exactly. Yeah, and like these ones were canceled out, right?
Yeah, and then
Yeah.
so since we know it's right, we do the stuff over there.
Yeah, blah 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 blah. Add them together, you get a big blah blah blah.
Yay!
Yay! Okay, but do you get this process now? Like
Yeah.
how you choose this 2NO? Because that's probably the hardest part. Like realizing that this has to be 2NO over here on the left side.
Mm-hmm.
Okay.
I'm so
Your
cool.
all drawings, unless you want to take a screenshot or something first.
Yeah, I just took a screenshot. Okay. Now, yeah. Okay, so are we done with that now? Let's this okay, what is Gibbs free energy?
Gibbs free energy is like it's kind of wait, what they say about Gibbs free energy that you need to do?
Okay, so he had this thing review. It's like he said this is the 4 things that you should know. Tell me if you know them or not.
Is it these
So
ones?
uh
Delta G equals delta
I
H
don't
equals
know.
delta S.
He just said we need to know specific heat enthalpy has as long Gibbs free energy.
Okay, Gibbs free energy, basically what it is it tells you whether a reaction is spontaneous or non-spontaneous.
Okay.
So tell me this. If you leave
What does spontaneous mean?
I'll tell you. So if you leave a block of ice in a room,
Mm-hmm.
will it melt?
Oh yes,
So
spontaneous
that
means like
reaction is spontaneous. It will happen.
okay.
If you leave bleach on
Oh.
a shirt, will the bleach get rid of like the color and kill the shirt?
Yes.
Yeah, it will. If you have those heat packs that you
Mm-hmm.
take to Tahoe, you know how you have to shake them and then they
Yeah.
get hot? If you don't shake them, will they get hot? Will the reaction happen?
No. So that's non-spontaneous.
Non-spontaneous. Yeah. If you have like a yeah, now do you see the difference?
So spontaneous is yes, non-spontaneous is no.
Yeah. So if delta G is negative, that means it's spontaneous.
Okay.
And here is a reaction to find this is a equation to find out whether something is spontaneous or not spontaneous. So if this side ends up becoming negative, then it is spontaneous. So it will happen. So let's go over the example of melting ice or some shit, okay?
Okay.
So let's look at that reaction. Okay. So the delta H of melting ice. So remember we went over this? Does it get does the surroundings get hot? Okay. When ice melts, is the delta H negative or positive?
It is it's a
Okay, think of
sound.
an
Yeah,
example.
wait, yes, it's the positive.
It's positive. Okay.
Yeah, because the final temperature, because like it's going upwards, so the final is yeah.
Okay, so it's delta H, so it's some positive number, okay?
Mm-hmm.
Minus T and then delta S. So delta S is spontaneity. So does it get more messy when the reaction happens?
Yes.
So like liquid's more messy than solid, right?
Yes.
So that means delta S is positive. If you're going the other way, like just think about it. If you're like making ice from liquid, do you see how it's less messy? That means delta S would be negative, which means that the entropy is decreasing. So delta S so S is about entropy. Entropy is like the disorder or like the messiness kind of.
Mm-hmm.
Another thing is that hotter things are usually like higher. Actually, no, I won't go there. Just think of it in terms of messiness. Okay. So now let me ask you this question. And then okay, what T stands for is temperature.
Mm-hmm.
So if you want this to end up as a negative number, So you have a positive minus a positive. Is there any way to end up to make that end up as a negative number?
Positive minus a positive, right?
So if you make this number, this second
This,
part bigger, right?
yeah,
How do you make that bigger? You can manipulate the t.
more messy, right?
Okay, so you can't manipulate this number. This number that's a positive, the spontaneous reaction, that delta S will always be the same. This delta H will always be the same for that particular reaction of melting ice. So the only variable you can change is this T, agreed?
What is the T?
Temperature.
Oh, just need to make the temperature higher.
So if you make the temperature higher, this number gets bigger, agreed?
Mm-hmm.
So a small positive number minus a big positive number results in a delta G that's negative, which means it's spontaneous.
Mm-hmm.
Which makes sense, right? Think about melting ice. Do you think it happens fast? Do you think it's more spontaneous at high temperatures or lower temperatures?
The higher.
Higher. Okay, now let's
Yeah.
say now let's say that this T was a low number. Let's say it was like the temperature was like -10 or some shit. Or actually no, not -10. This is in Kelvin. Let's say like it was like 2 Kelvin. Then this would be a very small number, which means that it would be a positive. The delta G would be positive, and then that would mean that it's not spontaneous, which makes sense, right? Like ice won't melt at low temperatures. It'll only melt at higher temperatures. So do you see that? That's how you should be approaching these problems. So try to predict what its delta H would be based on what the reaction is, and then try predicting what its delta S would be based on how much messy it is.
Okay.
So let's say you had some reaction that like you have like 2 gases on the left and you like end up with like 10 gases on the right.
Mm-hmm.
Oh, you know like dry ice?
Yeah, it's like if you touch it, you're dead.
I mean you're not dead, like
Your fingers are
fine.
dead.
But like
Once you're like, once it like stick to your thing and like you,
okay, okay.
whatever.
So let me give you a bunch of examples. You have to classify the delta H as being positive or the delta H like or the delta S being like positive or negative, blah blah blah. So dry ice, what happens in this reaction? You know like how you can see like steam coming out of it and stuff?
Yeah.
Okay. So do you think the disorder is increasing or decreasing?
It's
Is it getting more messy?
yeah.
Okay, so is the
Yes.
delta S positive or negative?
It is positive.
Okay, so I'm gonna look at this chart right here and put a plus sign over here, okay?
Okay.
You see this?
Yeah.
Okay. Do you think the delta H is negative or positive for this reaction?
It is uh so is it is negative? Wait. It's negative, right? Because it's melting?
No. Think about what it does to its surroundings. Is it releasing energy or absorbing energy?
It is releasing.
Really?
Yeah, so this is what the steam is coming out because it's releasing energy.
Is it cold or hot?
It is freezing cold.
Okay, then it's positive.
Uh,
Because do you see how that's absorbing energy then? Because if you feel something is cold, that means it's literally sucking your energy out of you. Like if I touch an ice block, do you see how like the heat from your hand is like going into there and your hand
yeah.
is left cold? That means it's absorbing energy rather than releasing it. If you have a firework, do you see how that's releasing energy? It's making you hotter
Yeah.
if you touch it. So that would be a negative delta H. So now what you do, since you found out that these are both positive, just look at this column, this row, and copy it.
Okay,
Positive,
so
positive, match it up to this, and then copy it down.
negative positive depends on high temperature.
So
It will
delta
be a
G,
large factor.
negative. So spontaneity, it'll be negative at high temperature. So do you see how it says high temperature favors spontaneous?
Mm-hmm.
So you can be like delta G is negative at high temp. See that?
But
Like, see how you can just read this and kind of copy it?
yeah.
The delta G is negative because it says spontaneous at high temperatures. So like this is stuff that you should be able to do based on just like matching it with this graph. Okay, like they might give you other examples, like I don't know, explode, like burning a coal or something. Yeah, let's say you're burning a coal. Tell me everything about this reaction.
It is negative H. It is getting messier. So it
Okay,
is negative, it is positive
which
S.
row does that match up with?
The first one.
Okay, so copy this down. Spontaneous at any temperature. So it really
Mhm.
doesn't matter if you do this at like freezing temperature or like super hot temperatures.
Yeah.
This is always spontaneous. So like okay, then answer me this. Why don't coals just burn randomly?
Because they haven't been ignited.
Yeah, exactly. So they haven't reached activation energy. So once you once like one of them is ignited, like a small part of it, the rest will ignite. That's what it means by spontaneous. Like, yeah, it hasn't had the ignition yet, but like it's still trying to do that, you know? But meanwhile,
Mm.
if you like try lighting like water on fire, nothing's gonna happen, right? So
Yeah, unless you had
non-
oil.
that's like non-spontaneous then. Okay, does that make sense? Like everything here?
Mm-hmm.
Yeah, so it's pretty easy. You
Mm-hmm.
just like match it with the row and you just copy it. So that right there is Gibbs free energy.
Mm-hmm.
Okay, let's go up. Yeah, change in entropy. So this section tells you like exactly how to do everything. Change in enthalpy, yeah, exothermic, endothermic, you know that. Change in
Mm-hmm.
energy. Okay, also think about it this way. So they might give you a reaction. So number 2 is kind of like a harder one for students to get. Like let's say you have some reaction where it's like, I don't know, 2CO2 on the right side, like as a gas, plus like, I don't know, like, I don't know, freaking H2O liquid. And it ends up being like 3 moles of gas on the right side. So like, I don't know, 3H2 gas on the right side. Do you see how there's more moles of gas on the right side than the left?
Yeah.
That means this is more disordered than the left side. So the hierarchy of disorders, gas is the most disordered. Like, do you see how random it is? Like, what the
Mm-hmm.
heck? And liquid, at least, like, it stays in the cup, you know? So
Yeah.
that's, like, slightly less disordered. But then, like, solid, like, you can keep it. It's just, like, not going to do anything. It's not going to change shape. So that's the most
Mm-hmm.
ordered. So look first at gas changing. So do you see how there's more gas on the right than the left?
Mm-hmm.
Is this more messy or less messy now on the right?
More gas on the. That's more. If you add more gas on the left, then it's less messy.
But you have more gas on the right. So this is more messy,
Oh
right?
yeah, more messy.
So is it a delta S positive or negative?
It is positive.
Exactly. So this delta S is positive if there's more gas on the right side. So that's what this less gas mole to more gas mole means. Okay, what if
Mm.
there's no gas involved? Like what if there's just liquids and solids?
Then it is less messy.
No, like okay, let's say there's 1 mole of liquid on this side and like there's 3 moles of liquid on this side, 3H2O on this side. I don't
It
know.
is messy then, since
Yeah,
liquid is messy.
yeah, exactly. So then the next step on the priority list is liquids. So since there's more liquids on the right side than the left and everything else is solid or something like that, then it's more messy on the right now. Get it?
Mm-hmm. Yeah.
Perfect. Okay, solid to ions in solution. So that's kind of obvious too. If you have like a block of salt and you put it in water, that's going to be a bunch of ions now, right? So you see how these ions are moving around randomly too? So if you
What
like
are
dissolve a
what are
solid,
ions again?
like if you have NaCl, do you know what that is?
Oh, that's salt, right?
Like table salt. Like you know how it's crystals?
Yeah.
You put that in water. What does it turn into? What happens when you put salt in water?
Salt water.
Yeah, exactly. Okay, I need to go now. My other class is starting.
Okay.
But yeah, bye.
I can see